that goes through this edge, then your polygon must be completely on one side of this line, either to the left or to the right. Doesn't say much. It's one of the definition of one of the algorithm to compute convex hull takes the intersection of all the half planes that contains your set. So for convex polygon, for every edge in a convex polygon, the whole polygon lies on one side of this edge, either above or below, on one side of the line that passes through this edge, that contains this edge. Hopefully I'm not creating any controversy here, which means what? Let's look at the line through this edge. And it defines a half plane, which a polygon is on one side of it. Let's make an attempt to use green once again. Look at the line that will this edge. Again, how did I pick these two edges? That are the two edges that my vertical line probes. And of course, Q, the green polygon, is on one side of this line completely. Which means what? Can I know right now whether P and Q intersect or not? Absolutely not. But what I'm showing that based on the direction of these two half planes, if I'll go to the left, then they definitely, if I move my sweeping line to the left, then they definitely don't intersect to my left, because they are bounded inside these half planes, so they are pushed away from each other. If I have a hope for intersection, it must be to the right. So I spend log n time to get the answer of yes, they intersect right now, or go to the left or go to the right. So go to the right will be pick a vertex that is to the right, maybe this guy, and pick a line through it. Well, now I don't hit Q. Pick a vertex right here. Pick a vertex right here. Then now my sweeping line says they still don't intersect, but now you need to go to the left. So after log n many probes, you find two edges that are intersected, or you're sure that they don't intersect at all. Okay, and that's how we're getting to log square n. Other questions from homework one that you want me to mention?
Is the solution going to be posted?
In?
The solution for the homework one going to be posted or no?
I usually speak about it in class. I think that people understand way better when I'm highlighting it, and I prefer that if I'll ask it again in the midterm, then you'll have to say, yes, I understood what it is, rather than I cut and paste the posted solution. But I'm very patient in discussing it. So if you have other questions that you want me to discuss, there was another hand. Yeah?
Could you go over 6b?
Remind me?
It's the one where you have to like find a line that perfectly divides the vertices.
Happily. So the whole trick is that now if I have a vertex, a line that divides the polygon, I need to estimate how many vertices there are over here, which once I find it, I know where all these two vertices are in the sorted array. It will be Pi and Pj. If I'm going counterclockwise along this polygon, then it will be maybe Pi here and Pj here, if I'm in this scenario. But sometimes I also want to know how many vertices there are between Pj and Pi separately. That is, in the if I start from Pj, how many vertices there are until Pi, and that would be this plus this. So you just need to count either the vertices between the I and j or the vertices that are after I and coming before j. I warn you that there is always at the beginning of the course this little twist that the polygon is in cycle order, but I store it in just an array in linear order. So it affects my binary search, like it affects my binary search and so on. So that was the solution to this part. Other questions? Perfect. We can talk about it more later. Let's continue with linear programming. Any question about homework 2 already? Were you about to say?
Yeah, I couldn't quite get that. Actually, it was, I think, the vertical line or horizontal line. And we need to compute
Yeah, if it's
where is the b. So I think like y is equal to b. I didn't get that for how we compute the b.
If it's a vertical line and you want to divide them, then you will ask, for example, if it's vertical line, I'll find what is the leftmost point and what is the rightmost point to start with. The rightmost point will be one of the vertices here. So right now I'll just change my I and j to, because it's a vertical line, that would be pi. And the rightmost point, that would be pj, which now implies that I can start doing the binary search, and there is a little trap here. I start to do binary search, for example, on the vertices on the upper part. So when I'm picking a vertex from the upper part, I'm finding where it is in the lower part, and asking right now how to do binary is for every vertex, essentially along it, or in the sorted list. I can find how many points there are to its left, how many points there are, how many vertices are to its left from each one of the halflets. The moment that you think about this array as two arrays that are one from the top, one from the bottom, you don't really need to spend the linear time to separate them. You just imagine that everything that happens here is yet another array that is sorted modulo the circularity.
Yeah, I mean, like, let's say you have a horizontal line,
Mm-hmm.
and like 12 points are at the bottom, and like 100 points are on the top. How we can move this b to some point that half of them are to the bottom of this line and half of them?
So there must be a vertex. What I'm not sure ahead of time is if this vertex, that is a crucial one, is at the lower part or at the upper part. So I'll try to do the binary search of the lower part, each time probe and check how many vertices, how does it divide the other vertex. If I'm picking the middle, we start. If I'm picking the middle vertex between in the lower part, then I know that in the lower part there is half and half. I need to figure out how does it divide vertices at the top, this line. And once I know how many vertices are here and how many vertices are here, again it says go left, go to the right. What I'm not sure is that if I'm just limit myself to go to using vertices on the left, maybe from this vertex A, I'll have too many on the left. From this vertex B, I have too many on the right. So I need to now refine my search by going to the upper side. I'm not sure ahead of time if the critical vertex is the vertex that I'm looking for. But the tricks that I can always give me a good line, and I can always shift it to the left or shift it to the right until it hits a vertex of the polygon. So it's enough to check only vertices of the polygon itself. There is it's again the standard trick of moving from a spectrum of infinitely many solutions to only discrete n squared polynomially many solutions. Okay. Linear programming.
Quick question. Like for finding where it intersects on the top part, can that be done in constant time, or is that log n?
Naively it takes log n. You need a few more tricks to make it actually in linear time.
Okay.
Explanation next.
I can't remember what the time complexity for that problem was. Was there log n? Because if it takes the log n just to find the
What?
point,
That was description with log square n.
okay.
That required searching just in the case of the two intersection polygons.
Okay.
Okay.
Can we get like a written version of the log square?
Sure. For this problem, one problem is happy. Okay. Integer linear programming. So we talked about linear programming in higher dimension. We said we can move from 3 dimensions to 2. If we have linear programming in 2 dimensions, we solve them using the randomized incremental algorithm. We solve them via solving one or many linear programming in 1 dimension. Moving from solving the 2D by calling the 1D solution. We also discussed if I want to solve linear programming in 3 dimensions, we had a slide for it, then we might add one half space and at a time. And if we find one that violates the solution that we had so far, then we need to call the 2-dimensional linear programming now, which in turn might call the 1 dimension, and so on. And in homework 3 and in general, I might ask problems where I'll use the very same algorithm, where I don't necessarily try to find an optimal solution. I just want to ask either a solution or not. For example, I'll ask you a little puzzle, probably I'll ask you again in homework 3, but in the meantime, you can play with this. I'll give you a set of vertical segments, and I'm asking, is there any line that crosses all these vertical segments? That's very, very similar to a question that I do ask you in homework 2, to ask, is there any line? And you can say if there is a line, then there is a line with a maximum slope or the minimum slope, and use linear programming for this problem. Sometimes I'll just ask you find a line, if there is any. It is possible to find a solution to this problem or not. And then you can use whichever cost function that you want, but linear programming tells you the feasible solution is empty or not. Okay. In 4, 5, 6, 7 dimensions, probably you'd like to use a simplex algorithm and the simplex library that tells you a linear programming problem. Here is your solution or not. Very practical, very fast, efficiently. And we mentioned integer linear programming. So integer linear programming is just LP where all or some of the vars are integers. So are required to be integers will be a bit better phrasing. That will be integer linear programming. Of course, you can ask what if some are not all of them, then it will be mixed integer linear programming. Many variants But the good news about all these problems is that there are a few libraries. Cplex is owned by IBM and has thousands and thousands of experts or years worth of trying to optimize libraries that solves these problems. So if problems that you face in your real life can be phrased as an integer linear programming, then by using these libraries, you have a much better chance to see a solution instead of trying to solve it yourself, to try to come from a heuristic yourself. And since 99.999 something % of the real life problems are NP hard or harder, and the rest are mostly trivial, then it's actually very good news. And what you're sure about the integer linear programming, each one of these libraries, is if it spits a solution, again, since you're solving a NP hard problem, you're not guaranteed to have a solution. But if it spits a solution, then it will be an optimal solution to your integer linear problem. So let's give the general definition of integer linear programming. It will usually be find variables, vector x, which would be x1 dot x2 dot xd. So now I live in the d-dimensional plane, in the d-dimensional space. X bar vector, list of small xi's. In 2 dimensions, it will be x and y, x, y, z, and so on, but such that AI vector dot product x is small or equal than bi. AI and bi are given. In the diet problem, AI was a vector that told you how many vitamins there is in it, how many vitamin A1. One was a constant that told you how many units of vitamin 1 there is in a banana. And A1, 2 was how many units of vitamin 1 there is in an orange. And making it a vector AI just make the notation a bit easier because I might have more dimensions. So the different i's in the diet problem refers to different vitamins. And AI is given, BI is given. What happens if I have a half play, if I want to refer to the same thing, but my constraint is AI x is larger or equal than BI? Well, just multiply both sides by minus. So instead of AI, use minus AI, instead of BI, use minus BI, but the direction of the inequality swaps. So by only writing in this way, I don't limit my generality. It's a bit sunny, the fan starts working. And the OBS somehow reset itself. Sorry, OBS. If I want to write an equality here, you can either say that it's exact equality, or you can write it as two inequalities. AI is both larger than B and both smaller than B. And these will be my constraints. I go from 1 to ... n. And I want to minimize the cross product of C times X. C is a cost vector. In the diet, it was how much a banana cost and how much an orange cost. And C dot product X, the dot product, was how much do I pay for bananas and oranges combined, given that I eat X and Y values from each. And finally, if you don't want to eat, in this solution, the solution to the linear programming, the pure linear programming, might say that you need to eat 0.34 bananas and 7.9 oranges, and you might find it impractical or to buy 7.9 oranges, which is less practical. So you might add the requirement that x1 dot 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 xd are all integers. And when you told your libraries that you want to have this requirement that all the xi's are integers, then the running time will be larger, maybe much, much, much larger, maybe intolerably larger, but you only get integer solution. You have to buy only an integer number of oranges and bananas. Since I don't feel that this class is too worried about the diet problem, let's talk about other questions. Let's see general problems from graph theory. All the classical problems that you might have seen in other courses, probably have seen in other courses. And my input to this problem is a graph. What is a graph? Set of vertices, cities, edges, yada yada, and a set of vertices. Every vertex might be a location, might be a point, is a plane, whatever you want to think as a vertex. And to make it a graph, I have to set what are the edges, which pair of vertices I look at. That would be the graph. So E in this case would be the edge B6, B5. B6, B5 will be one of my edges. B6, B4 will be another one, and so on. Every pair of edges. That's a general graph. Who is friends of whom? The graph might be directed, or that is it. There might be an edge from A to B, but there might be a different edge from B to A, or undirected. In this case, my graph is undirected, it's completely symmetric. And let's talk about one problem that is a hard problem, which is to do vertex cover of the graph. What is a vertex cover? Find the minimum cardinality vertex cover, which is, when I'm looking for vertex cover, I'm looking for a set of vertices so that I hit every edge. Pick a set of vertices so that every edge of this graph has one of the vertices that you pick. Solution, pick all the vertices. Pick all the vertices. It's a vertex cover. Fine, let's publish it. Now, if we want to publish more results, maybe we want to find the smallest vertex cover over them. And finding the minimum cardinality vertex cover is hard, NP hard. You cannot expect to live long enough to see it being solved for really large inputs. So let's phrase it as a linear programming. I'm not going to solve this problem, definitely not to present a polynomial algorithm, which would be very nice. Instead, I'm just going to show you that if you have an access to a library that solves vertex covers, and you can also, that solves integer linear programming, then you can take a graph and make an integer linear programming problem out of it, which is 99% of the work that you really have to do to find an optimal solution. By the way, before I proceed, which vertex, let's copy this graph. So, we will be my vertex cover over here. There is a lot of cells that, for example, take all the vertices. But I don't need to pick all the edges. But what's the minimum size in this graph? 2. But I can pick this vertex to be in the vertex cover, and then I cover this edge, so I can kind of delete it. And then I still have the issue of covering the other edges. Pick this guy and this guy, and then I'm handling this 3 and maybe this and this. Voila, that was not very efficient, but it solved my problem. A better solution is probably to pick vertex 4, and which handles everything that leaves 4, and I'm only left with the edge 5, 6. So, well, pick this edge. So the minimum vertex cover is here. Now, good news is that it's not very hard to get factor 2 approximation. Meaning what? Even though I don't solve the whole problem, I want to just find a solution which would be no more than worse the optimum. And I want to find a solution that is not more than twice the optimum. What will I do? I'll pick an edge, and I'll take both of its endpoints into my vertex cover. Why is this justified? Because either this vertex or this vertex might be in the optimum. Optimum paid 1, I paid 2. And then I'm getting rid of all the edges that I just succeeded to cover. So I just cover everything here. And I end these ones. And now I'm just left with this edge. And I pick both of its vertices, because I don't know which one is correct. And I'm done. So I paid 4 vertices, 1 per each vertex in the solution. And the optimum solution has size 2. And it's at most 2 and not exactly 2, because possibly the optimum solution is exactly what I picked. What if my graph looks like this? And I started by picking these 2 vertices. I start by picking this edge and both its vertices, then this is actually the optimal solution. So it's at most factor 2, but it can be approximated. Okay, now let's see how do I phrase it as an ILP problem. So the ILP problem for this point will be, I'll assign a variable xi, and we're a bit leaving here computational geometry and moving to algorithms in general. I'll assign a variable xi to each one of the vertices. So the number of vertices that I have is the number of variables. The number of variables will be the number of vertices. And I'll say, what do I tell the ILP about every xi? One of the constraints, convince yourself that it can be it can be stated in the same way, is I want xi to be between 1 and 0 for each one of the xi's. Oh, and by the way, that's a linear constraint, 2 linear constraints actually. And I'll add another one, that xi is an integer, which doesn't leave xi a lot of options of what it can be. It can be 0, it can be 1, and that's all the integers between 0 and 1. Okay, well, how is this related to my problem? I'll understand that if xi will be 1, then vertex I is in the solution that I'm after. And if xi is 0, then this vertex is not in the solution. So far, I just said how I interpret it, how I understand the relationship between the vector xi's versus my original problem. Now I need to tell the ILP some constraints. That is, how is this related to my graph problem? And these constraints will be different depending on my graph. But what am I going to do? I'm going to pick each edge, vi, vj, and write xi plus xj, the vertex, the variable of vertex I plus the variable of vertex j. They should be larger or equal than 1. They can be larger than 1, they cannot be smaller than 1. And I'll do it for each one of the edges. What does it mean? Why am I writing it in this way? What do you want the vertex cover to do about the edge B6, B5? To be a vertex cover, either B6 must be in your cover, or B5 is in your cover, but either X6 is 1, or X5 is 1, or they're both 1. It's also fine. So this constraint is justified. Right. So I'll write it for each constraint, just to be a bit less abstract. For this graph, it would be x1 plus x4 is larger or equal than 1. That takes care of the first edge. x2 plus x4 larger or equal than 1. Let's jump into the last edge, maybe x5 plus x6 larger or equal than 1. Great. And so far, the ILP will tell me pick all the xi's to be 1. It's a perfect solution. That's exactly what you need. It is a vertex cover. It satisfies all my conditions. But that's telling you ahead of time. Now I want to tell the ILP also what is my goal. I want to minimize the number of vertices that I'm taking. How do I write it in a way that ILP understands? I'll just ask minimize x1 x1 plus x2 plus x3 plus x4 plus x5 plus x6 for this problem. That is, your cost function consists of 1, 1, 1, 1, 1, 1 for this problem. And then you're calling ILP to solve it, and most likely you'll get the solution for the right problem. Okay, and here, and again, it will probably do a better job than what you do solving it directly. There's another problem. The minimum weight vertex cover. My graph is the same graph as before, except that now to use a vertex, I'll assign some weight, some penalty that you need to pay to use a vertex. And it's individual per vertex. You can take B6 to be in your cover, but that will cost you $4. So W4, the weight of vertex 4, of vertex 6 is $4. The weight of vertex 5 is $9. If you solve the problem polynomially, even if you could, it will make it into different level of difficulty. In terms of the ILP, it's a piece of cake. What do I change in the ILP to find a vertex cover that minimizes the weights of the vertex that I'm using? I will just solve exactly the same problem as before, except that I now minimize Wi times xi. So my call, it's only in the cost function that instead of being 1, it will solve my problem very nicely. Let's spend 2 minutes and I'll show you something really cool. Did everybody buys my approximation, the factor 2 approximation, for the unweighted case? Pick an edge, take it. Pick an edge, take it. Pick an edge, take it. Take both its vertices and delete all the edges that you already stubbed. and continue. And that gives you factor 2. You're not paying more than twice. Let's see something cool about this one. I don't know of any such simple heuristic for this problem. So so if I want an exact solution for the weighted vertex cover, all I can do is to solve the ILP exactly. And ILP, because it's NP hard, maybe it will run in reasonable time, maybe not. Depending on what's the complexity, what's the input. But there is another thing that I can do. Again, I'm willing to settle for a factor 2 approximation. Solutions for which the sum that I'll pay will not be more than twice the optimal solution. What should I do if running the ILP is too slow, but but I don't have an elegant, straightforward approach to get a constant factor approximation, that is a solution that is not more than a factor, not more than 2, the optimal. I have another solution. We said LP always runs fast. Simplex, you need to work extremely hard to create exponential running time. And they are very, very unstable, not with general position. It's really hard. The complexity of the simplex algorithm is, in the worst case, exponential, but it's extremely rare in practice. And actually, there are proofs that say that it has smooth analysis, meaning you'll add a bit noise and all this exponential behavior will vanish. So linear programming will work fine. That is, I'll solve the very same problem, except that now I don't require the xi's to be integers. I'm still using these constraints. Xi is between 0 and 1. I'm still using these constraints. And now you're running the LP, not the ILP. And possibly the LP that runs very fast, no matter what the input, possibly the LP tells you this is the optimal solution, gives you it tells you it solves the linear programming without the integer. It solves the integer linear programming at which you can assign third of the weight for this vertex and 3/4 of the weight for this vertex. This problem will be solved optimally. The weighted integer linear problem, the weighted vertex cover. All cool, but I need to know what is the set of vertices that I'm going to use at the end. It's for each vertex, I'll either use it or not. So here is the trick. So I pick X, which is the solution to the LP. I remove the integers and it suddenly runs fast. And now I'll define a vertex vector Y where Y, which would be Y1 dot 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 Yn, where Yi equals 1 if xi is larger than half, larger or equal than half, and it equals 0 if xi is smaller than half. And now if yi is 1, then vi is in the cover, and if yi is 0, then vi is not. Okay. Now I need to explain, or I need to justify a few things. I need to justify what is a cost, what is sigma of sigma of yiwi. That's the value of the cost, how much I'm paying for the vertices that I do take. Yi is integer. Sigma of yiwi is smaller or equal than, what do? For every xi, if it's larger than half, I take xi, here is 0 and 1, and I'm looking at half, and I'm looking at xi. And if xi is larger than half, then I'm rounding it to be 1. At most double its value. If it's smaller than half, then I make it 0. So you only sum up here the values for which the xi was already half. So this is at most twice than sigma of xi wi, and we said that's the opt. It's the opt for the float integer linear programming, that you are allowed float, and this is by obviously smaller than the solution to the real weighted vertex cover. The float means you don't need to use integers. So you paid at most twice. But that's less exciting. What I need to really justify to you is who said that this rule, that I am picking a vertex only if its yi is larger than half. How do I know that it's vertex covered? Help?
When xi is over 1.5, then yi is 1. Then it means that the vertex vi is in the cover. So the solution should be also be the solution of the vertex.
Right, but how do I know that there are no edges that I missed? How do I know that every edge was hit by one of these vertices?
I think still.
That's the heart of this argument.
Still the constraint that 0 or xi plus xj is greater than equal to 1.
Which implies that, look at the edge vi, vj. But what's the meaning of this constraint? Could it be that xi is 0.3 and xj is 0.2, both smaller than half? If they are both smaller than half, xi is smaller than half, xj is smaller than half, then when I sum them up, I'll get a value which is less than 1. Solution for the LP forces for every pair ij for which ij is an edge, either xi or xj must be larger than half, or at least half, meaning that you will take them. Every edge will be hit, and you're paying at most twice. I think that it's pretty cool. Everybody understand? Yeah.
Why is that one the optimal solution?
This will be at most twice the optimal solution for the LP. Now, what is the relationship between the opt float versus opt int? We want the opt int, which says take the solution to the opt part, and then you want to minimize the sum of weights, you want to minimize this number, but then in addition you are adding more constraints. But for the int, it's exactly like the opt over here, plus it's exactly the same problem, but I'm adding more constraints, making my solution, of course, more expensive. But I force variables to have more conditions on them, so my solution space is smaller. So I'll have to pay more. So it's, to be precise, you see at least twice opt float, which is in terms at most twice opt ILP, which is opt to the solution itself. Okay, let's slow down the pace a bit. Let's talk about the art probably gallery problem. I think I updated the slides. Let's see if Dropbox catches them. Never mind, didn't see. So let's talk about the art gallery problem. We'll talk about the art gallery problem a few times during this course. Let's define the art gallery problem, actually our next topic. Extremely important problem for many applications. In the art gallery problem, I have a polygon or some environment. Maybe it's a polytop, maybe it's a building, maybe it's a terrain with mountains, and there are points that I need to guard. Maybe it's every point in the polygon. Here, for simplicity, I'll assume that I only need to guard the vertices of the polygon. Just for simplicity. How do I guard them with? I want to place guards in this subproblem. I'll place guards only at vertices. That is, I'll pick a guard that would be right here, G1. I'll pick a guard that would be right here, G2, and so on. And what is my requirement? As I mentioned, I think, in our very first meeting, I can say that a point P sees Q, a point P sees Q in the polygon if the line of sight between them doesn't hit any obstacles. So P sees Q, but P does not see Q prime. If I put Q prime over here, then if P is watching toward Q, I cannot see through a wall. Okay, so and you can add limitation constraints to it. You can say here are just points that I can place cameras that will watch the whole part. Oh, I didn't tell you what's a problem. I want to pick guards so that every vertex of the polygon will be seen by one of my guards. So here I'm placing guards only on vertices, and I'm watching only vertices of the polygon, but I might as well do it for any point in the polygon. Applications of this problem, of course, placing cameras that watch the whole area of the building. We place a polygon by a building, and that's your problem. Another problem is look at a terrain, mountains, and place cellular antennas. So you got best coverage, you got coverage everywhere, and you are using minimum number of antennas, various other sensors, and so on and so forth. And I'm proud to say that, to the best of my knowledge, the best algorithm for this problem is mine, lots of years ago, mine in quarters. But let's ask, how can I use ILP to solve this problem? this problem, like anything interesting, is NP hard. Finding, so just to phrase the problem, given a polygon, find a subset of the vertices so that every vertex is seen by one of these subsets, one of the guards. And in addition, you're picking as few guards as possible, unweighted case. Just minimize the number of guards. In a convex polygon, how many guards do I need? One. Every point will do the job in a convex polygon. Are there non-convex polygons that one guard is sufficient? Again, can you show me, draw one example where one guard is enough, but the polygon is not convex? And your answer is?
A star. Oh.
A star-shaped polygon, there is such a thing, and we'll talked about it a few times, about knowing if a polygon is star-shaped. There is a point here that sees everything, but it's not. It's polygon. We are in ILP, so let's write down how do I find an ILP problem for this problem. So I'll pick a vertex A, and I'll ask, what is the visibility of A? What are all the points that A sees? What are all the points that A sees, which are in terms that potentially sees A? And let's add to it that these points are also a vertex. So I'll write the visibility of A as all the other vertices that sees A. So if I'll use the star-shaped polygon, then A sees B and C and D. If I'll draw a line from A to D, maybe no. I'll include D in it. I'll definitely include F. I'll definitely include G and H. But I don't see this point. But line of sight outside the polygon. A sees H, B, F, and G. So these are A equals, of course, A itself, and G and H, and B, and in my example, C. If I do it right, so the line of visibility between them, yeah, a bit on the border. That's about my general position. There is a theorem that says that every time that you're drawing 5 points, there is a line, 3 of them will be collinear if you're drawing them big enough, or just not trying very hard not to do it. So, yeah. So let's say that's the part now I want to find an ILP. To find the minimum set of guards so that every vertex is covered. Every vertex is seen by one of my guards. So I'm using these two words, guard and a vertex. But a guard is just one of the vertices that I picked, that I place a camera on it. Okay. So a guard must be on a vertex, but not the other way around. And trivially, a guard sees itself. How do I make an ILP out of it? So I say every vertex VI, as usual, I'll assign a Boolean value, xi, where if xi is 1, then I'll place a guard at vertex vi, otherwise I will not. Which means in terms of ILP, xi is between 0 and 1 and is integer. What's my constraints over here? So I first need to compute, I assume that it's taken place. I know for every vertex what is its visibility region. Which vertices does A sees, which vertices B sees, which vertices C sees. That's already computed. Now, what is the constraint that A imposes? What is the constraint that you see right here? The constraint that A by itself imposes. I have x of A, x of B, x of C, and so on. Actually, in this case, plus x of A plus x of G. X of G, just instead of using indices, I'm saying that's a variable that is assigned with G, 0, 1. Plus x of G plus x of H plus x of B plus x of C, if that's a visibility polygon of A. What do you know about this sum? If I did find a set that sees everything.
At least once you can see all these vertices from A. So at least
These are the vertices that A sees, which is in turn all the vertices that sees A. And that's an exclusive list. There is nobody else that sees A among the vertices. So if I pick a guarding set, one of these guys must be in my guarding set for A. So this plus this plus this plus this must be large or equal than 1. That was to satisfy that somebody sees A. And similarly, I'll do the visibility of B, visibility of C, and so on. I want to minimize, I want to guarantee that for every vertex, somebody sees this vertex. Somebody in its visibility region is being selected. By saying that it's larger or equal than 1, it means that I don't mind if I pick 2 vertices from here, but at least one of them should be picked. If none of them is picked, then nobody sees A. Nobody sees A is unguarded. Okay, so I'll add constraints like this for each one of the vertices. And what am I trying to minimize if I just care for the number of vertices? It will be minimize the sum of the xi, the sum of the guards that you are using. Where this algorithm is extremely useful, it's less so if you want to solve the art gallery directly, because ILP might be really large in this case, especially if you have a lots and lots of points, but you're definitely using it if you have another algorithm and you want to ask, how is my algorithm compares related to the optimal solution? The ILP will spit the best art gallery for it. So if you're trying to market your algorithm as a really practical solution, then you'll say, here are a set of problems that I did run the ILP comparing to them, and all my solutions were only 5% more expensive than opt. Okay, moving for 4 minutes to our next topic of well, so a bit more about graphs and connectivity and Euler formula, and then we will see a really, really cool the art gallery here. And what does it? Okay, I'll worry about this next time. OBS claims that something is wrong, but it will have to manage somehow. Okay, we are having a graph. Before, you have a set of vertices, you have a set of edges in this graph, and let's talk about topics that we already touched on, like the connectivity of the graph. Let's talk about the degree of a vertex. Degree of a vertex is just how many neighbors does it have. My graph is not connected. You are my neighbor if I am your neighbors, and vice versa. How many guys are you connected to? We talked about faces. And by the way, it requires a proof, but the graph is an abstract thing. The embedding is the actual painting of this graph. It's where I place it in the plane. If I was drawing it without any crossing, then now I have faces of this graph. And surprisingly, no matter how I drew the same graph, it will look completely the same with slight little difference. The outer face might be different, but the graph will stay the same. A graph is connected, not surprising, a graph is connected if between every pair of vertices you can walk while you are staying only on edges of the graph. If I can go from one vertex to another, then it's connected graph. You know what is a subgraph. Subgraph of a graph, pick some vertices and pick all the edges that connect them. If the graph is not connected, maybe this is my graph, this is not connected. It's not a connected graph from this guy. I cannot go to this guy using a path of edges. However, there is a bunch of other guys that I can go to. So this suggested the notion of connected components that is really important. I look at the vertex, I look at everybody that I can reach with path in this graph. Okay, connected component is just whomever you can pick by being connected. And it's possible that the graph is connected and then you have a single connected component. And it's possible that there are no edges at all, but a lot of vertices, and that every vertex by itself is its own connected component. Both are fine. And we're running out of time, so to be continued from this part. Thanks, everybody. Get back to me with